Hello, in this lesson, we're going to go over some homework questions. And so I prepared some examples, and some of them are directly from the homework, and some of them are kind of the optional work on the homework. And so let's get started. And I also prepared a flashcards. On this flashcards, I'm going to show you right now. So far, on algebra, so there are some of these flashcards are for from the algebra classes, such as, but we still use these properties. For example, there are 6 mathematical principles. The first one is that any number times 1 stay the same. And the second one, any number add 0 stay the same. And the third one is that if A is the same as B, then A plus C is the same as B plus C. And D is that number 4, if A is the same as B, then A multiplied C is the same as B multiplied C, provided that C is not 0. It's a very important condition. Number 5, if the product of 2 numbers is 0, then one of them must be 0. So all of these, and the number 6, which is the last one from algebra, is that it's about the product and the quotient, which we're going to use these properties very often. And so let's see, what are these properties? These properties are, the first one is the positive times positive stay positive. Negative times negative stay positive. Positive divided by positive and negative divided by negative. So these 4 cases, then when we have the same sign in product for 2 numbers, then it's always going to be positive. And if we multiply 2 quantities that are opposite in sign, and the product or quotient will be negative. So these are the flashcards that we use often. And the next set of flashcards I prepared for you is about limits, right? So we have covered all of these concepts, intuitive definition of limit, and one-sided limit, and the theorem about the relationship between limit and one-sided limit, that relationship. And the direct substitution limit, intuitive definition of an infinite limit, and intuitive definition of a negative infinite limit, and limit laws. Okay, vertical asymptotes, and then limit laws. Okay, so we have all these limit laws and the theorems that we have covered. Oh, wait, this one, I think, okay, this is correct, okay. And let's see, what's the next one? The limit laws, that one. Okay, so those are the things we have not covered in this week. So just up to this number 17, okay? So when we are going over these examples, then sometimes we are going to refer to these flashcards, and at that time, the flashcards will be brought to our attention. All right, so let's get started. The first one is that we want to find the limit. We want to find the limit. And this limit is a quotient. And obviously, this quotient is one polynomial divided by another polynomial. Okay? So we have that direct substitution method. So can we directly substitute, right? So you might be thinking out aloud. So if we can directly substitute, that would be amazing, right? So when we try to, I'm going to have something called think out aloud. Think out aloud. Think out aloud is my scratch paper. This is my scratch paper. Okay. But on think out aloud, I will naturally check. Can I apply limit law? Can I apply the direct substitution? Because if I can do that, question will be solved very, very quickly. So I will be checking the denominator. I'll be checking the denominator. Okay. And the other thing you might be thinking of, right? If I said, well, let's substitute. Okay, so we're gonna check if I substitute the 4, will I get not equal to 0? Because if it's not 0, then we can use direct substitution. So I'm gonna roll up to direct substitution property. Where's direct substitution property? Right here. Okay, so this is direct substitution. We're thinking if I can use that. But to apply direct substitution, then I should guarantee the denominator is not 0, right? Because this is a rational function. If the denominator is not 0, that means the number is in the domain. So one way to check it is to plug in the denominator. And then I plug in, I found I get 0. Because 16 minus 4 is 12, minus 12 is 0. So this tells us that we cannot use direct substitution, nor we cannot use the quotient law. We cannot use the quotient law either, right? There's a quotient law. And quotient law is right here. We cannot use it either. So then what do we do? Right? In this case, we cannot use either one of these properties. We have to do something. We have to do something algebraically. All right. So with that in consideration, of course, you can also think of the domain, right? You can think of the domain. Domain consideration will also help us to draw the same conclusion, because 4 makes the denominator equal to 0, so 4 is not in the domain. Okay, so x cannot be 4, right? X cannot be 4. So all of these considerations, whichever one that is most convenient for us or most convenient for you, right? X cannot be -3 either if you want to set up, to find the domain. So, but -3 is, away from 4. So we're just observing the behavior of the function in the neighborhood of 4. So this doesn't bother us. Okay, so in the neighborhood of 4, we can't do anything convenient. So what do we do next is we're going to use our algebraic skill. We're going to use our algebraic skill, which is factoring. We're going to factor the top. Okay, factor the top. The top is factored into, let me make the font a little bit larger. Okay, the top is factored into x times x plus 3. And the bottom is going to be factored into x minus, let's see, x minus 4 times x plus 3. Okay, I think those are the factors. Let me see if I got the question. All right. Okay, all right. So let's move forward. As x is approaching 4, you know what? I think okay, let's just do it. Okay. As x approaching 4, and certainly x plus 3 is not 0, so we can reduce these two factors. Okay, so we can reduce these two factors. We get the next expression. So x plus 3 and x plus 3 are reduced. We have x over x minus 4, right? Now what do we do? X is approaching 4. We have reduced the function to x over x minus 4. Then what do? We cannot reduce any further. So then we say, well, there's nothing we can do. How about we look at the limit from left or right? Right, we look at the limit from left, from smaller than 4, and we're going to look at the limit from x approaching 4 from larger than 4. As we look at these limits, as x approaching 4 from smaller than 4, x minus 4 is going to be negative. X is going to be approaching 4, so the numerator is going to be positive, close to 4. Denominator is going to be negative. So the denominator getting larger and larger, getting closer and closer to 0, but it's negative. So this is going to be approaching negative infinity. When x is approaching 4 from larger than 4, right? The numerator is approaching 4, a fixed number, and the denominator approaching 4 from larger than 4. So x plus 4, x minus 4 is going to be closer to 0, but positive. So this is going to be approaching positive infinity. And this can also be confirmed if you draw the picture. If you draw a picture. Okay, so we can draw the picture. So from the picture, okay, make it right here. Okay, so from this picture, in the neighborhood of 4, you can see our evaluation is confirmed. So this just tells us x equals to 4 is a vertical asymptote. It's a vertical asymptote. So we actually have a vertical asymptote. But what is the answer to the limit, right? So let me just draw this vertical asymptote to show you. Okay, just draw you the vertical asymptote to show you. Okay, and I will just make one more adjustment to show you a better picture. And over here, we're gonna have maybe 9, negative 20, positive 20. So from this picture, we can see the limit when x is approaching 4 does not exist. Okay, does not exist. That's it. You can see to work out one question, actually it requires some time and patience. Requires some time and patience. And this one doesn't have a limit. Then it doesn't have a limit. Okay. All right. So the first question is done. Okay. So feel free to use the scratch paper and feel free to pause during the lesson and do your calculation before or after. So let's look at the second example. The second example, we have right here as x approaching 4, x approaching 6, we have a function 8 minus half times x. This is a polynomial. Right? So we can use direct substitution. We have a direct substitution right here. So we can use direct substitution, right? So to show our work, all we have to do is just directly substitute 6 into the function and calculate. Then you can see the limit sign being dropped, right? And in the end, we get 5. Oh, that's all you need to do. That's all you need to do. Direct substitution. So let's look at number 3. Number 3. Actually, I might have copied the question wrong. No, I did not. X squared minus 2x minus 8, x minus x minus 4. Sorry, this I did copy it wrong. X minus 4. Okay. And on this one, obviously, not do not direct substitution. It's the same consideration, right? We cannot do direct substitution. We cannot do limit law because x is approaching 4, denominator is approaching 0. So we have to resort to algebraic manipulation. So we work on the algebra part. Factor. Okay, so the top will be factored into, let me grab that sign, okay? We get x minus 4 times x plus 2. And the denominator is x minus 4. Because, right, so here I want to bring you the intuitive definition of limit. Intuitive definition of limit. That's the flashcard we're using. When x is approaching 4, but x is not 4, right? X can get to 4 as close as possible because 4 is not in the domain of the function, right? So as a result, x minus 4 is not 0. Since x minus 4 is not 0, we can reduce it. When we reduce it, which property are we using? We're actually using the first flashcard. We're using the first flashcard. The first flashcard basically says anything times 1 stay the same. X minus 4 is not 0. So x minus 4 divided by x minus 4, that's equals to 1. So as a result, we have reduced x minus 4 in our expression. Yes, we only left with x plus 2. Okay, and then what do we use? This will be direct substitution, right? And when we use direct substitution, actually we have a very, very useful theorem. Yeah, this theorem, we use it all the time, and very soon, actually, we're going to kind of just not mention it soon. But at this early stage of learning limit, I do like to mention this theorem. This theorem is saying, okay, hold on, this is number 17, yeah. So you can see this function and the original function given, they are the same except for one point. That point is x equals to 4, because the domain of this function is x cannot equals to 4. But the domain of this function is all real numbers. So these two functions are only different by 1 point. And when we take limit as x approaching a, which is 4, that point is a critical point that they're different at, and that's the only point they're different. And they have the same limit. So we actually use this theorem on the right. The direct substitution, so 4 plus 2, that equals to 6. All right. All right. So let's look at number 5. No, number 4. Number 4. Number 4, we cannot do we cannot do any reducing. I think I might have copied the question wrong. This is x minus, it's x approaching 2, and this is x approaching 2. Okay. All right. So we cannot use direct substitution. We cannot use a quotient rule either. So what can we do? Oh, we can try our algebraic manipulation, right? So we're gonna do some factoring, right? So the top is factored into x plus 1 times x plus 4. X plus 1 times x plus 4. And the denominator was x minus 4. But there's nothing can be reduced. nothing can be reduced. Then what can we do? What can we do? X is approaching 2. X approaching 2. Well, in this case, then what's the use of the factoring? What's the use of the factoring, right? So in this case, we will have to, so the factors could tell us what do we expect in terms of sign, right? And so we are going to consider limit from left. Limit from left, approaching 2 from left. We're going to consider approaching 2 from right. So under the circumstances, as X is approaching 2, the top is going to approach a fixed number. That fixed number is 3 times 6, right? 18. The top is going to be approaching 18. But the denominator is going to be approaching 0 from smaller than 0. So this is going to be approaching negative infinity. And the other one would also be approaching positive infinity because they have the same numerator, which is approaching 3 times 6, right? 18. The denominator is going to approaching 0 from larger than 0. So this is going to be approaching positive infinity. And if you have any doubt about our analysis, we can draw the picture. We can draw the picture. Okay, so let's look at the picture. Let's look at the picture of the graph, right? As you can see, this function is doing pretty well elsewhere, but in the neighborhood of 2, we have a vertical asymptote. We have a vertical asymptote. So let me draw this vertical asymptote to show you. And we're going to draw, excuse me, the vertical asymptote, which is so you can see this vertical asymptote pretty well. And also, it is not defined right there, right? So our algebraic knowledge will help us to understand that. So let me just give you a little more view on the higher up. Vertical asymptote. And of course, our vertical asymptote will go even higher. Okay, there you go. So that's the vertical asymptote. So obviously, this function does not have a limit. Okay, so you can say that does not exist. Does not exist. Okay, so that's example number 4. So you can see in our examples, some has limits, some don't. And we have to use our algebraic skills and the definition to analyze. So let's look at the next one, example number 5. Example number 5. I don't want to make this too long. So at a certain point, we're going to stop and we're going to continue on the next episode. Okay. And this one, obviously, we will think of product. We're gonna be thinking of a quotient rule, direct substitution, or you know, either way, right? Does it apply? So we're gonna think out aloud. So the key of the question is the denominator. Denominator cannot be 0. Otherwise, we can do, direct substitution. So we're going to substitute x by 4. Let me double check. Actually, you know what? I have just changed 4 to -2. Okay, I made a copy error. So from that, yes. So x the point of interest is -2. We want to check if -2 will make the denominator equal to 0. Okay, so substitute into the denominator. And does it equal to 0? Well, let's find out. Okay, so this makes 4, so this times 3, that's 12, minus 10, minus 2. That's going to be 0. We cannot use direct substitution nor quotient at all. We have to resort to try algebraic manipulation. All right, so what do we do? Factor. The top can be factored. And let's see what the bottom can be factored. You may like to pause at this point, okay, to see if you know how to factor the bottom. Okay, the bottom seem to take some energy to factor. So we try to factor this piece. Okay, so we factor, what do we get? I'm going to try to factor this, and I try a couple of things. This is our algebraic skills. So we're going to try to factor, and I try a couple of things. And I found I can factor this into factors. Okay, let's see if it works. So it's going to be wait, did I get the top? Yeah, the top, wait. Never mind, I think I delete what I did earlier. Sorry about that. Okay, so we got x plus 2 times x minus 3. Sorry about that. X minus 3. The bottom, we're going to get x plus 2. Oops. X plus 2 times 3x. I didn't want to go over the factoring techniques, but I will verify that. If you need lessons on factoring techniques, I will make another video. But here, I'm just going to assume that you know how to factor, okay? So please let me know if you need more help on this. So I got these factors, and it's great to see that x plus 2 are common factors, so we can reduce it. Okay? When x is approaching 2, once again, it's the fundamental, it's the theorem, right? I'm sorry, the intuitive definition of limit. X is approaching -2, but x is not -2. If x is not a -2, x plus 2 is not a 0. So we can reduce these two common factors from top and bottom. We can even drop the parentheses. Now, by this time, once again, another drill that you know, right, is that we have applied this theorem, right? They have the same limit. And also, you notice that this ladder function, the domain is x not equals to 1/3, i.e., if I substitute -2 in the denominator, it is not going to be 0. So now we can apply direct substitution. Okay, so where's my direct substitution theorem? My direct substitution theorem right here. Okay, it's a rational function and -2 is in the domain. So the next step is straightforward, direct substitution. So to do direct substitution, what you can do, and I'm just showing you how to show work, okay? You can drop the limit part and bring -2 to replace x. That's how you write it. Okay, replace by -2, and then you reduce it. Okay, the top is -5, the bottom is -7. So -7, right? The end is +5/7. Okay, when you show your work, you don't have to show all of these. Okay, and the factoring part, you don't have to show. You don't have to show, even though you need to know how to do them. Okay, the kind of work we like to see is pretty much just this much. Okay, so think out loud part usually is my scratch paper, and you don't need to show your work on the scratch paper. All right, so let's look at the next one. Number 6. You can see I have prepared quite a few questions for you. One more time. We cannot do direct substitution. We cannot do quotient. So we have to do factoring, right? And factoring for power 3, we have to know some algebra. So let's do the easy part, okay? T squared minus 9. Okay, t squared minus 9 is t minus 3. This is very commonly used factoring scheme, which is a squared, right? Let me put commonly used factoring formula. Okay, one of them is, of course, is a squared minus b squared equals to a plus b times a minus b. So a plus b times a minus b. This is a very useful formula. Okay, so that's what we use, because t squared minus 9 is t squared minus 3 squared. How about t squared to the minus 27, right? This one, we obviously learned that in algebra, but sometimes we just kind of forgot, okay? So to factor that piece, this formula, you know, actually, I don't always remember all of it, so I just play around with it. And you're allowed to do that because there's something called scratch paper. There's something called scratch paper. So a to the power 3 minus b to the power 3 is equals to a minus b multiply, I think it's a squared plus ab plus b squared. Have I forgotten? Is it right? Well, to verify is it right or wrong, I just have to FOIL this, right? So I'm going to verify for myself. And you can pause and do the same, right? So I'm going to verify. So a times a squared, that's a to the power 3. And a times ab, that's going to be a squared times b. And the plus a times b squared is ab squared. Okay? And I'm going to verify more because I'm going to take the negative b times a squared, negative b times a squared. So I'm going to have negative a squared b, right? Negative a squared b. Negative a squared b. And negative b times ab squared, that's going to be minus ab squared. AB squared. And the negative b times b to the power 2, that equals to minus b to the power 3. So I've verified, and because these two make 0 and these other two make 0 as well. So I have just verified my formula. Okay, but these formulas is not hard to find, right? They're pretty commonly seen. Now, so t to the power 3 minus 27, I'm going to work with that. 27 is 3 to the power 3 equals to, right? So I'm just going to copy the formula. Capital A is t, right? So this is t and this is 3. So this is t, whoops, t. And this is what? A times d, that's 3t. And that's going to be 3 squared, right? So I'm going to put my factored form in place. Okay, and 3 squared is 9. 3 squared is 9. All right. Keep going. We can reduce t minus 3, but once again, like in the intuitive definition of limit, t is approaching 3, but t is not 3. T get close to 3 as much as possible, but t will never be 3, especially 3 is not in the domain, right? So we can do the reduction. So t minus 3 will be reduced. And we can even remove these parentheses. Now, right, a couple theorems already being used. What can we do? Direct substitution. Direct substitution, right? Because this is a rational function and t equals to 3 is in the domain. So we can remove the limit. Just replace t by 3. And simplify. Okay? So let's finish this question. And let's see what we get. This is 9, this is 9, and this is 9. We have 27 on top. The bottom is 6. Can we reduce it? We can reduce the 3, right? We can reduce the 3. So 3 go into 27. That's a 9. 3 go into 6. That's a 2. And finished. 9 over 2. Okay, that's example number 6. Now let's look at example number 7. Okay, number 7. Number 7, we encounter the same issue. Obviously, we cannot apply limit law and we cannot do direct substitution because as h approaching 0, denominator is going to be 0. So we cannot use any one of those properties. But we have a radical on the top, right? Typically in this case, we try to rationalize. So we find the conjugate of the top. The conjugate of the top is the root plus 3. So we constructed a 1. Okay, so this is number 1. I'm going to bring you mathematical principle number 1, right? So anything times 1 that stay the same. So we have conjugates. So let me just give you a little review of conjugates, right? Any two number, a plus b, has a conjugate. Its conjugate is a minus b. They are conjugates to each other. I'm put a plural here. Okay, they are conjugates. What's so nice about conjugates? We just had a formula here, right? When you multiply conjugates, right? If I put the left on the right, right on the left, we're gonna get this. When the conjugates multiply each other, we get one number square subtracting the other number square. So it's a very nice property we used a lot in algebra classes. So in our case, right, 9 plus h, 9 plus h, minus 3, that's a minus b, and its conjugate is these two. Let's just change the sign, right? One is a plus, one is a minus, that makes the conjugates. So that's the property we're using here, okay? So let's move forward. Equals to, so now I'm gonna multiply the numerator with the numerator, denominator with denominator. So this denominator is gonna multiply the denominator right here, right? So this is left with 1. So numerator times numerator. So we got, we bring them a little closer. In fact, this step can be omitted. This step can be omitted. I just want to show you. So this step is optional. The next step is really what I want you to show you, what I want to show, okay? Because we're going to apply that a squared minus b squared, right? So we did that. And that equals to a squared minus b squared. Okay? So a minus b times a plus b, that's a squared minus b squared. We apply that. And this step, let me mark it. It's optional. It's really because we didn't really do much there. Optional. So for those of you who want to save a step, you can save it. Okay? So now what is the root of, there's some other algebraic information I'd like to bring to your attention. Okay? One is that if I have x squared, okay, x is any real number, and that equals to the absolute value of x. Okay, the square is inside. Okay, the square is inside. So this piece actually does not apply here, And we have another one. The square is outside. And what does this equal to? Equals to x. And you say, why? Why? Right? Well, this is addressed in the previous lesson, right? Because what's the difference between these two? The difference between these two is that the domain for this one is all real numbers. The domain for this piece is x greater than or equal to 0. So the square, whether it's inside or outside, makes a difference. And which one applies here? The latter applies to our situation because the square is outside. So as a result, this piece is just equal to 9 plus h. It is 9 plus h. Okay, so this one does not apply, and this one does. Okay, because the square is outside. So square inside or outside makes a big difference because the domain issues. I'm going to put this under here, put on the note. Okay, what's the difference between these two? Right, so before we proceed. This piece, the domain, is all real numbers. All real numbers. And this one, the domain, because the order of operation, right? So order of operation. On this one, you need to do the square first, right? You need to do the square first. And after you square any real number, it's going to be at least 0. And this one, you have to do the root first. In order to do the root, you have to guarantee x is going to be greater than or equal to 0. So that's why we have these two different situations. All right, so let's go back to continue. Simplify. Well, 3 squared is 9. So 9 minus 9, that makes 0, right? So we only have h on the top, right? So not negative 9, take away the 9, we just have h. And then what about the h? H and h reduced. H is approaching 0, but h is not 0. Therefore, we can reduce it. So now we can do direct substitution because we no longer have any issues with 0 denominator. And we will just directly substitute. You can use Quotient rule, whichever you like to use, right? Some people like to write it this way, which is okay, why not, right? The limit of 1 is 1. So some people would like to say, hey, I'm going to bring this limit to this form. Basically, you take limit on each individual term. Boom. That's not going to make any difference, right? And we're applying limit law, and that equals to, in the end, here, we're going to do direct substitution. For that direct substitution, we're going to have 1 over root of 0 plus 9 plus 3, right? So in the end, we get 1 over 6. That's the end of the question. That's the end of the question. So you can see in this question, we also take the opportunity to review some key concept in algebra. Okay, some key concept in algebra. Okay, so let's do one more, and then we're going to take. We're gonna stop and continue on the other one. So this is a complex fraction. So we have fractions in the numerator and x minus 3 in the denominator. Can we apply any limit laws? And nothing. No, we can't, right? So it's obvious. We have to handle the complex fraction. Once again, we know x approaching 3, but x is not 3. So we're going to use a technique to reduce the complex fraction. So how do we reduce the complex fraction? Algebra skill. Okay, so we're going to multiply common denominator. So this is a one fraction, another fraction, and all of these, you can see the common denominator is 3 times x. So we're going to use 3 times x over 3 times x as 1. Anything times 1, so we apply this mathematical principle. Anything times 1 stay the same. And then we take 3x to multiply each one. Right? We take the 3x to multiply. Boom. Right? So that's what we did. And reduce it. X and x reduce, so we have 3 minus x. Okay? The first step, we did quite a lot. Okay? Let me put this one over here. That equals 2, right? And then we're going to reduce this piece. How do we reduce it? This requires a little algebraic skill. 3 minus x is negative x minus 3. Okay, so if you forget about this piece of algebra, you can verify. Okay, you can verify, but you don't need to show this work. is 3 minus x is equals to negative x minus 3, just in case you don't remember that part of algebra you learned before. That's okay. You can just verify on your own time on your scratch paper. Your teacher don't need to see this. Okay. Once we have done that, right, x minus 3 reduced. Oops. And then we ended up with direct substitution because this is a rational function. And 3 is not in 3 is in the domain. So we're just going to substitute x by 3. So in the end, we get negative 1 over 9. Negative 1 over 9. Okay. I want to take a break here because I don't want to make each video too long. And so I will continue to talk about examples in the next recording. Thank you for watching.